All right. Yep.
Yes, sorry for the dog noises you hear throughout the rest. It just has tempers. But anyway, welcome everyone to After Hours for CSEU4. Today the plan is to go over hash tables a little bit and blockchain at the end of that. Can you guys hear me?
Yeah, we can hear you fine.
All right. Yeah, so I'll start with hash tables and then Melky would finish up with blockchain. Um, So for hash tables, I plan to go over three things. I'm sure we are familiar with concept of hash tables, but this is just like a revision of sorts. So I'll go over what hashing means, then what an hash function should be, and then finally I'll close off with hash tables and then solve a problem using hash tables. All right. So I'm going to share my screen now. One second. All right. Um, So like I said, I'll start with hashing and then hash functions, then hash table, and I'll solve like a code challenge at the end of this. So first, I'm sure we're all familiar with hashing from like backend development, where because you can't save passwords as plain text in databases. So when you get a password, you have to hash it and then save it. And then on subsequent logins, you hash the password and then compare the hashes. So hashing basically converts things from one form to another, or from any data format to like a string, really. That's what hashing does. And most times, hashing is irreversible. So once you hash something and you get the hash, you can't go back from the hash back to the original thing just because of how hashing works. So it turns out that hashing is really useful in lots of things. And yeah, thanks to hashing, we're able to use hash tables, which are a very, very effective data structure, a very efficient data structure just due to how fast they are, because they give you constant lookup time. And that's something that is really, really, really needed in lots of algorithms. So anyway, so hash table really is a data structure that maps keys to values using a hash function. So we have hash tables here. It stores things as key value pairs. So it takes in a key and then using a hash function, it's able to convert the key to an index and then stores the value at that index. That's really what an hash table does. And for a hash table to be efficient, it has to have a good hash function. And to have a good hash function, there are some things that your hash function should be able to do well. The first is that your hash function should be deterministic. So what this means is that given the same inputs, we should always give you the same outputs, because when you're trying to hash something, or when you're trying to add something to your hash table, you pass in the key, it hashes the key to an index. It means any further time that you supply that same key, we should give you that exact same index. So that's like the most important thing for your hash function to work well. It has to be deterministic. The next thing is that your hash function should be distributed. So it means it shouldn't give you the same values. So you try and hash, let's say you try and hash boy, it gives you index 5. You try and hash girl, it gives you index 5. Yeah, there's probably a problem with that, because your hash function should, given a particular bucket size, it should be able to spread things across all elements in the bucket, like in kind of a uniform manner, because that helps reduce collisions. And collisions is something that are really, really messes with the lookup time for hash tables. So you try and reduce collisions as much as possible. And a key attribute to achieving that is by having a distributed hash function. And the final thing is that your hash function confined, so it should exist in a particular range, and it shouldn't go above it. Of course, since remember for hash table, the underlying data structure is always an array. You have some sort of array, and then everything happens with the array. So if your array is 5 elements, your hash function should always return a value between 0 and 4, because you're going to store it in the array. So those are like three properties, right? Those are like three properties that you need for an efficient and for a good hash function. And realistically, you wouldn't be writing your own hash functions just because of how difficult they are to get right. So in most cases, you'll be using one that has already been pre-written and has been well tested and that is reliable. And I guess the popular one that you must have used is the DJ Bit2, I believe it's called. Yeah, and um, yeah, so DJ Bit2 is of course the popular hashing algorithm which seems to work really well for strings. So whenever you are hashing, right, whenever you're hashing strings, DJB2 comes to mind just because of how well it works and how distributed the hashes are. So let me just try and find a DJB2 implementation and show you guys. So this is the DJB2 implementation. It takes in a key and the output is a hash. The hash is probably really large. Let's just try it. I'm just going to print hash DJB2 for some random key. Let's just try random and let's see what we have.
Yeah, it's the self there.
Yeah, so you see, you have a really large value, like really large. And if I just add something small, let's say I add just a dot after random, then it changes completely. Like it's not even close. And yeah, so that's so. And the way DJ bits work really is you have a particular number already 5281. For some reason, I mean, it's not really proven because you wouldn't really see lots of resources explaining this. But for some reason, and from testing, it turns out 5281 just works really well for it. And what you do is you multiply your hash, this 5281 by 32. All right, and then you add the ASCII value of each character in your key. So that's really what you do in this JB2. Like I said, you wouldn't really find too many resources explaining why it works this way, but it just works and it gives you reliable results. So that's a hash function. So there's this site that I want to bring up now. I'm trying to find it. Okay. Yeah. So this kind of just shows you a hash table and how things are added to it. So remember, in a hash table, the underlying structure is an array. So in this case, we have an array with 12 items, and everything that you're storing in your hash table is added to this array. So now, let's assume we're going to store ONE first. Okay, let me make a string ONE. When you insert it, what happens is that it converts ONE, yeah, converts ONE to a particular hash index, which falls between 0 and 12. In this case, it was 11, and it adds ONE to at index 11. All right. So let's add something else. Let's add to TWO. When we say that it gets index 3 and it adds TW as index 3. Let's add the next one, 3. This goes to index 12. And then I've 4.
Can I
So,
ask a question?
yeah, sure.
What algorithm is it using to hash?
Yeah, I'm not sure what this uses in particular. I'm really not sure, but it's just something.
Okay.
It's probably, yeah, I'm really not sure, but it's something. It's an algorithm. It just converts the key to a number. And you can see up here that this is open hashing. What open hashing means is that when you have collisions, you add the collision to the same hash table. So you chain the collisions. So that's what happens here, because when we added 4, there was a collision on index 3 because we already had 2 there. So what happens is, since each element is like a linked list node, so we just chain collisions at that same index. If it was closed hashing, this wouldn't happen. This would probably happen in another hash table, and then we kind of keep track of um, of the duplicates. But we open hashing, which is a little bit easier. We just store things as a chain. But then remember, if you have a not so good hash function and you have lots of collisions, whenever you want to retrieve, it's possible the worst case becomes big of n, because you have to now start searching and you lose the functionalities and the benefits of using hash tables. So that's why the importance of a good hashing function cannot be overstated. All right. So any questions so far about hash tables?
Earlier you said we cannot go back from the hash to the value.
Yeah.
I know that's true, and I think I know why, but can you elaborate if you know? Like,
Yes. So remember to hashing thing. The way it works really is you have a number 5381, and for each character, for example, if you want to hash boy, for instance, I want to hash boy. For each character in boy, you multiplies this hash by 32 first. Just this is the same as hash equals hash times 33 and 32 plus or right. Let me just comment this out for the exact same thing. So we want to hash boy. So hash initially is 5381. So for each element of each character in boy, he multiplies hash by 33, and then he adds like the ASCII value of B to hash. Then does that same thing for O and does it for Y. So it means by the time this is all done, we have a particular value in hash, which is a large value. Now, you can't really go back from that value, because number one, you don't know how many characters were in the initial key, because all you're doing is adding, and then it's possible that a different word, let's say cop, can give you the same let's say ZZ, because ASCII values rise as the letters rise. So like Z has a bigger ASCII value than B. So let's say ZZ and BOY have the same sum of ASCII values. So it's possible that this ZZ give the same hash as BOY. So now, how do you know which one is which? So that's why hashing mostly is like a one-way operation, because it's kind of impossible. Yeah, let me just say impossible to go back from a hash to the original value, because you have no idea what it was. All right.
another question. So, like a few years ago, they told us to stop using MD5 because there was too many collisions, and nowadays it's the same for SHA1 and maybe even 2. Um, any idea how to reduce collisions on our own hash table implementations?
Yeah, the thing is, with your hashing algorithm, it's mostly like a compromise between collisions and speed, because depending on the implementation, if you try and reduce collisions too much, there's a likelihood that your algorithm takes too long to complete, and that's what you don't want. So that's why you still see like SHA-512 and others being used just because they're really fast. And like I said, in most cases, you wouldn't be implementing your own you wouldn't be implementing your own hash function. So I mean, the popular one that we've used is bcrypt, right? So that's what we use for password hashing. Yeah. So and it works really well. It's fast enough, and it doesn't really collide that much. So so yeah, like this whole thing is like a different study, like cryptographic studies, which is like really really in depth. So if that's something you're interested in, you can always go into that. Right.
Cool.
Yeah. So I'm just going to copy over a hackerrank problem now that uses hash tables, and we'll try and solve it together. All right. So this is a problem. It's called ice cream paddle, and I just I just searched for hash tables there, and I picked like the first problem that I saw. So what this is saying is that each time Sonny and Johnny take a trip to the ice cream parlor, they put their money together to buy ice cream. And on a given day, the parlor offers a line of flavors, and each flavor has a cost. Given the value of money and the cost of each flavor, 40 trips helps Sonny and Johnny choose two distinct flavors such that they spend their entire pool of money during each visit. So reading this line, something jumps to me. It says, help Sonny and Johnny choose two distinct flavors such that they spend the entire pool of money during each visit. So it means we're looking for two numbers that add up to the money that they came with. All right, just keep that in mind. We have ID numbers are one based index number associated with the costs. And for each trip to the parlor, print the ID numbers for the two types of ice cream that Sonny and Johnny purchase as two space separated integers on a new line. You must print the smallest before the biggest, right? So an example, if we have 5 flavors, and this is the cost they have. So they have 21356, and they have 5 money. So what it means is that we're looking for two numbers in this array that sum up to 5. So in this case, 2 and 3 sum up to 5. And since it's one based index, so 2 is index 1, 3 is index 3. So the output is 1 and 3. So any suggestions on how we can approach this? It doesn't have to be optimized or anything. Just let me know what you think. So remember the goal really is to find two numbers in this array that sum up to the money, which is 5 in this case.
They say to print the smallest one first, so I was thinking before everything we order them, but then I noticed that we cannot order because the IDs will switch, so we have to use it as
Yeah.
it is, and
Yeah.
we switch them in the end.
Yeah. So any ideas of how to find two numbers in an array that sum up to index 5? I mean, one possible way you can do is you start from index 2, then you start looking for what you add to index. So you start from number 2, and you start looking for what you add to number 2 to give you number 5. So it's like you have like nested for loops. So you start with index 2, you check 1, you check 3. Assuming 3 wasn't here. Let's assume 3 wasn't here. So you check this, then you check this. If you don't find it, you go to index 1, you check this, 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 you check this. Then go to index 3, you check this, 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 then index 5. So eventually, when you find two numbers that match, then you know you found your desired outputs. But there's a problem with that because it's kind of slow. It's big of n square. And whenever you have something that you are searching for something, what comes to your mind immediately is hash tables, just because of how well they work with. Whenever you're going to memorize or whenever you're going to repeatedly perform the same thing, yeah, that kind of thing. Whenever you have this kind of problems, you're probably going to want to use hash tables. And honestly, in my experience, I've probably used hash tables the most whenever I'm solving algorithms because of how versatile they are and how fast they are. Because I mean, they're the only data structures that have big of one lookup, and maybe sets, and also sets use hashing like under the hood. So they're almost the same. But anyway, with hash tables, one thing we can do is we start from two. So with two, we know we need to find three because one is five. So we need two numbers that sum up to five. So we start with two, we want to find three. So once we find three, we know we've finished it, right? So we start with two, we store two in our hash table, so we don't have to search for it anymore. But what we want to do is we want to limit repeated work. So once we find two once, we never want to search for two anymore. So we can store these two that we found in a hash table somewhere. So let me try and bring this up. Yeah. So we have the hash table here. So remember, we've seen two is the first number. So we can store two somewhere. And we know the index two appears is index 0. So the value of this becomes 0. All right. So now we go to 1. 1, the complement of 1 is 4. Since the money is 5. Remember, we're looking for 5. So 1, what matches to 1 is 4. So we check if 4 is now hash table. It's not. So we add 1 to our hash table, which is our ones are index 1. Then we go to the next number, 3. And remember, money is 5. So we need 2 to match up with 3 to give us 5. So we now we check 2. 2 is in our hash table and it's index 0. So we just go to index 0, pick up 2 and 3, and we have 5. So you see how much more efficient the whole thing is, because we don't have to keep searching when we can just store things we've already seen in the past. And whenever we need this, we just pick it, since hash tables have big of one lookup time. So and the funny thing is that this exact same implementation, I've probably used it in like 5 problems, if not more. Like I said, hash tables, they are really versatile. And once you really understand them, you find yourself using them in so many problems. But anyway, let's just quickly implement this now. All right, so we have the costs, which is the array, and the money, which is the output. So the first thing is we define our hash table. Remember, dictionaries are hash tables. Dictionaries are hash tables. All right. So now let's look through our array. That's costs. So for price in costs. But now since we want access to the index, because we're returning the index, not the actual money. So let's use enumerate so we can look through the index and the actual value. So for index, price, enumerate cost. So for each price, we want to first find the difference and check if the difference is in our hash table currently. So difference, so let me use complement since that reads better. So the complement for each price is like the final money. That's like the goal minus the current price. And then once we have the complement, we want to check if it exists in our hash table. And if it does, that's where we end. So if complements in hash table, and it says, all right, it says so we want to print the ID numbers for the 2 types of ice cream that Sonny and Johnny purchased as 2 space separated integers on a new line. So we print smaller and larger, smaller first and larger second. So let's make a new variable for the outputs. So output equals, for now, let's just randomly add them. So the index, the current index we are, I remember it's 1 based. So we have to add 1, since Python by default is 0 based. So index plus 1, and since the value is the index. In our hash table, we store the actual price as the key and the index as the value. So here we can just do hash table complement m+1. Now remember, since it has to be sorted, I guess I guess we could just sort it. I mean, this doesn't really have I don't think this has any downside really, since we know for sure output always contains 2 elements. So this I mean is going to be like constant time. But if this could contain an arbitrary number of elements, then you probably will want to do something different. But in this case, it's constant time, so it's not really a big deal. And then we just return. That's if complement is in the hash table. But if it's not, else we add the price as a key and the index as a value. So yeah, I think that's pretty much it. And then Rodrigo, remember we've solved a similar problem, like with this kind of very, very similar solution. Yeah.
I remember when you asked for the solution, I didn't remember that trick, and when you started talking, I immediately remember the trick.
Yeah. Also, when I saw this problem, like as I read the description, it just came to my mind that yeah, that's one way we could solve it. And yeah, let me just run.
But can you explain the +1? I think I get it. It's like
1 second.
Yeah,
okay.
I think you didn't print, you returned. Yeah.
Yeah, so I have to print output 0, comma, output 1.
I think you have to put a space. Oh, the comma, yeah, that's the space. Ignore it.
By default, yeah, it's a space. All right, so that works. So now the reason why I had +1 here, let's look at the example they had. So in this example, we have 5 months to spend. So in this case, it's 2 and 3 that sum up to 5, or because it's one based indexing. So they return 1 and 3, 1 and 3, not 0 and 2. And by default, Python is 0 based. So we have to add 1 to make a matchup. That's why I added 1.
Yeah, I didn't notice that part on the problem.
I'm pretty sure enumerates you can specify the index. I'll just confirm. Enumerates index Python. So we don't have to add 1 manually.
You could also already store it in the hash table already with a +1. And yeah, sure,
Yeah,
that'll work.
That will also work. All right, so it's in enumerate, you can specify the stats equals 1. So I guess we could just do that here. So we can just do stats equals 1. And we should be able to get rid of this. And let's see if it works. So yeah, it also works. So yeah, so any questions? Yeah. John, Rodrigo? Nothing?
John never said a word.
Nah, I don't have any question.
All right. Yeah, I think that's it from me. So Melky will come in with blockchain, just an introduction, because blockchains they are really complex and like a really wide topic. So and we have really limited time. So Melky just talk about the basics and we'll probably just go over an implementation. All right.
Yeah.
Let's make a new coin.
Yeah, we're gonna make one. Do you have a name for it? Let me share my screen.
Lambda coin.
That already exists actually, so yeah, all right. So yeah, basically, like Rodrigo said, one of the applications of blockchain is cryptocurrency, right? But there's more to it than that. We could also do like a archive and file storage system where you have a blockchain, but each block is a file, and it's like a bunch of versions of the file. There's also that. Obviously, there's more. There's like smart contracts and warranty claims and things like that. But yeah, we won't get into that. So yeah, the general look at it would be blockchain is like a linked list of dictionaries, meaning like if you think of dictionaries like hash tables, right? So you could also think of it like a diary or a spreadsheet containing information about transactions. So yeah, this is just some examples. And yeah, blockchain also uses a hash function. And yeah, we'll get more into that. But like Victor already said, it's like a string of numbers and letters, right? So that's your hash function. And yeah, usually it's some kind of mathematical function. And yeah, it really varies depending on your algorithm, right? But yeah, the mathematical depth of that doesn't matter here. So we won't go into that as well. So your blockchain, obviously, it's a chain of blocks, right? So a family of blocks is the blockchain, right? Basically, if you have one block, you have the genesis block, which is the name you call the first one in the chain. And from that point on, the blockchain is like the whole group of blocks, right? So, and a block is just a way, like a term for specific data, right? So, for example, oh yeah, and also yeah, the chain contains all the transactions, of course, right? So a transaction is the transfer of coin to another person's wallet, all right? Is there any questions so far about like these concepts of blocks and blockchain? All right. So this is just an example of a block, right? And you have like a dictionary like this, right? You could also, like I said, like this is a hash table implementation, all right? So a block could consist of the index in the chain, the timestamp it was created, the transactions made during that time, right? The proof, which we'll get into, and the previous hash, which means that the previous hash means that this block contains the hash of the previous one. All right, so you take all of this, you hash it, and you get the hash of this block, right? But yeah, the current one also has the hash of the previous one. All right, this is for security purposes. So if a person would try to let's say alter the chain in order to give themselves coins, right? They would have an easy time to do so if we didn't have this hash here, because they just go into this transactions array and just put their name and the new number of coins, right? And that's it. But with this hash, it makes it much harder because now they have to create a hash, right? And it needs to be a valid hash from the previous block. And then the previous block also has the hash of the previous block, right? So it's basically turning it impossible to break. Yeah, that. Is there any questions about this hash here?
Yeah, what's up with the proof? What's exactly the
Yeah,
proof?
the proof is next, right? So, for example, for you to mine a block, to mine a coin, for example, right? A coin would be like a block, let's say, and the proof of work is if you, the person that are mining, find that you've solved the problem that was given to you by some server, right? You've solved this block, so this block will be completed. You will get a coin, and the block will close, making so that the next block will start, and then everyone else has to restart their work. All right, so it's like a proof
I
that
think
you're the one that solved some sort of problem or challenge. It
I
can
think
be, yeah.
I think I just remembered. Not sure if it's specific to Bitcoin or all coins. The proof of work is you mess with the timestamp, if I'm not mistaken, and the hash has to have X number of zeros, right, to be valid, and
Yeah,
then
you
you have
could
to
do
try
that.
and try
You
to.
could do that. You could do any number of things
Yeah,
to prove your work.
yeah. I think Bitcoin is 17 zeros, like
Yeah,
17
yeah.
zeros, so which is like really difficult.
It's a huge hash
Yeah.
kind of thing. Yeah.
Victor, what does it change to try a new one? Is it the timestamp? I don't remember.
Yeah, well, since it's finding the hash of the entire thing, and things change. So the timestamp changes depending on the time you are. The index changes because other people are also mining different things. And yeah, so things change. So it means you keep trying, keep hashing, keep hashing, and then when you get a valid one, then you've mined something. When you get a valid one, the reward you get is like a coin.
Yeah.
So yeah.
So yeah, we'll get more into that. We'll also work with zeros, but not 17, just like 3. Yeah. So yeah, that's the proof of work. So yeah, it's proof that you've done something and the money is yours. And yeah, I've already talked about this. The reason why it's impossible is impossible to fake a block or to give yourself money is that you will have to generate all the hashes for the whole chain before someone else creates a new block. So that's completely impossible if your uh, hash is well done, right? So yeah, you can't make a million block hashes before someone else makes one. So yeah. That's the overall look at it. I'm not gonna code it right now, but I do have an example, right? I'll show it working. If you have questions about the code itself, let me know, because coding all of this from scratch would take like a bunch of time, and it doesn't really have much added value there. Right? So in the beginning here, okay, so first, this file is the server file, so it's the server side, all right? Because we'll have the client side as well, meaning that we have the server starting a blockchain, all right? And we have a miner person that is trying to mine some coins, all right? The server side, we're using hashlib to hash, right? JSON to return. We have some time and ID generations, and then we're using Flask to start the server. So yeah, it's a bit easier for small things, right? And then we're starting a blockchain class, and it has three things that happen when you start it, right? So you start the chain empty. There's also no transactions made, and we create a new block. So we create the Genesis block so that everyone can start mining, all right? And then we have another method. So here we have the new block method. Obviously, it creates a new block, right? So it can take the proof to verify if it's a valid one, and yeah, it can take the previous hash as well. And then yeah, we have just a bit of a summary of this, but the code itself is we create a new block, right? The index will be the length of this chain array, right? +1, timestamp here, and then the transactions array, the proof itself coming in, and the previous hash, all right? So if we don't send a previous hash, we get the hash from the last block in the chain, right? So what does this mean? This means that you can send any hash from any block in the chain to create a new block in the chain. It doesn't have to be the actual previous one. It has to be one of the previous ones, all right? So yeah, this is what it does, right? So if someone doesn't send the previous block hash, we just get the last in the chain, right? And then it resets the transactions, appends the block to the chain, and yeah, that's it, all right? Then we have the hash function. The hash function just takes a block, converts it to a JSON string, and returns the hash of it, all right? So you get some block objects as a dictionary, of course. So you have something like this, right? And then it converts it to a string, so it becomes like a bunch of stuff like this. And then it converts it to a hash, so it becomes like this, right? Make sense so far? All right, then yeah, we just have a kind of some other things to help us out. So the last block here is just it's like a property, just returning the last thing in the chain, and then the valid proof method is the one that actually validates what's going on. All right, so if someone sends some kind of proof to be evaluated, this will check if it's a good one or a bad one. If it's a good one, it will return true, otherwise false, and nothing is created, right? If it's true, a new block is created, all right? And yeah, what it's doing is we get our block string plus our proof, all right? We hash it, and we see if it has 3 zeros at the end, all right? Making sense so far? All right. And then this is just a bunch of boilerplate things, all right? So this is initialization of a Flask, right? This is just creating a new node ID for our computer. This is initializing the blockchain. This is the mine endpoint. So we have a post to this mine endpoint, meaning that this is where our miners will, this is the endpoint our miners will hit and send their proofs, all right, to see if they're valid or not. And then there's like 2 more. So there's the chain endpoint where everyone can see the chain, all right? And then again, the last block endpoint that just returns the last thing in the chain. So let's go over this mine endpoint. First thing it does it gets the data coming in, all right, and it checks if the miner sent the ID and the proof, all right. The ID meaning the name of the person that is mining, all right. And that's what this does, right? It's just error handling, all right. Then we get the proof, and this is where we check if the proof is valid, right? We create a hash using this last block, all right, and we make a new block. We need to create this hash before, because the new block also has the previous hash, all right. So the new block will have the hash of this one, all right. So yeah, and yeah, we can also send a response. So the response will probably just be like new block first, and all the things that were on that block, all right. And then there's the a little bit more of error handling, like if the proof is not valid, we say that it was invalid, or someone else already sent it before, all right. So that's it for the backend side of the blockchain. It's a very simple one, but yeah, is there any questions so far?
I have a few.
Sure.
Can you scroll up?
Yeah.
I think I missed one or two lines. Wait, can you go down? Just on the hash function. Okay, blockchain dumps. Yeah, okay, hash. So, can you go to line 127? If I'm not mistaken. Yeah. Is it just me, or since you called the hash of the last block, it will like call itself again and again? Like, because the hash of, no, wait, maybe not. I was thinking maybe the hash of that one, like to get it, you have to hash the previous one and then.
Well, they're saved, right? They're not. It's not like it calls itself, right? They're saved in the chain, right? For example, when a new block is added here, right? This previous hash key, right? It will have the text, right? The hash itself. So it's not calling hash again. It's only calling. Sorry. Yeah, here. So it's only calling hash once, right? And this last block was already created. This is the one that we're on right now. This is the last in the chain. But now, because the proof was valid, we're going to create a new one, right? So we're going to hash the current one and create the new. The other hashes were already computed. They don't call hash, right? They already are in text form.
Yeah, because of memoization, or however you say that.
Yeah, yeah, they're saved already. So the whole chain is both public and yeah, it's accessible by everyone. And I believe that happens. Yeah, it just works like that. You don't need to hide anything. You can save it, no problem. All right.
Yeah. I have two more questions, like a bit off topic, if that's okay.
Sure.
About your documentation, if you scroll up, are those comments like valid documentation? Yeah, like
well, they kind of are, but there's not like a plugin that generates it or something like that. This is just something that it was already typed for me, actually, because this is one of the projects we did last cohort. So This, yeah.
But if you call the function, does it tell you like all that stuff, that it takes a string? And...
Yeah, like if you view the function
Oh, it's
from,
just text.
yeah,
Yeah.
it doesn't really like work together with VS Code or anything. Yeah, maybe there's a plugin for that for sure.
Another question is the decorators. Like, I'm pretty sure Tom didn't teach us the decorators, and I still don't know exactly how they work or what they do. So
Yeah, a decorator is like a function that runs first than this one. For example, the property one, right? This runs first, and it says that this one is a property. So meaning that it's like self dot last block, right? But instead of when I call self dot last block to be like a static value, like a string or a list of something, it's a function. So when I call it, it runs this. That's it. This is because I have to update it without any specific updater method, let's say, because this property here always needs to be the last in the chain. But if I set it, if I set this self the last block like this, right, and the chain changes, this is not updated. But in this way, if I define the property like this, it will always run as a function, so it will always be updated. All right. Yeah, this one I'm not so sure. The static method, I don't really know much about it.
yeah, but from what I understood, the decorators take a function, and that's our function, right? And then they do stuff, right?
Yeah, so it works the same way as in memoization. If you have like, I'm gonna use the classic Fibonacci, right? If you have a memoize function, you can use it. So you could do def memoize, and you get a function, right? Okay, so I think this is probably not exactly like this, but it works kind of the same way. So this is your decorator, and if you define it like this, right, your F is this one, all right? So it's this one. Okay.
Yeah, pretty much.
It.
So like with decorators, you can make your own decorators like what Milky did. So like a function, and then you can attach it as a decorator to another function, and then it means the new function inherits like the functionality of the old one. But in this case, Flask provides some decorators that are useful. So that's what we use in some cases, like the endpoints one, and some other ones. But yeah, and like the static method one is just, I mean, it's not really unique to Python, but it just means like the method is like a property of the class, not the instance. So
yeah, that makes sense actually. Of course, I don't have the self here. Okay, so yeah, and yeah, like Victor said, you can make your own, and it basically it's just a way that you can do stuff before or after you call this function. So every time now you call fif, it runs this, all right, and it does the stuff you want, and then it runs the fifth, and then it does the other stuff that you might want. All right, so yeah, it's like a, I don't know, standard way of adding things without changing your function, because I don't know, maybe you wanted like something like this, a plate UI, right? And then you had a Fibonacci function. But obviously you're not gonna do like update UI here, right? Because it doesn't have not anything to do with Fibonacci itself. So you do it on another one, and then you run the function, and then like, I don't know, some other class like update UI, and then like send this return value and update the value. Okay.
Cool.
So yeah, something like this. All right. So yeah, backend side, I think we're done. So the only thing left is the miner, which would be something a person would use to mine this specific coin. So yeah, I'm gonna just go from top to bottom again. So yeah, same thing here with the hash. All right. Then we have the requests library. It's just like you could call it like Axios or something, right? Then yeah, again the time, the system, and JSON. All right. We start at 0 coins. Obviously, if this was a bit more complex, we'd have like a first like connecting to a specific wallet or account, right? And then that's where we'd start mining, right? So, but yeah, let's just say that I'm already logged in and I start with 0 coins, all right? And then there's just two methods, functions here, all right? So first one is proof of work. So this is the one that tries stuff until he finds something that is valid. And then there's a validator, right? The valid proof. So based on the, good documentation on these coins README, right? We know that we need a hash with 3 zeros, so we make this hash, right? And then we make our function that runs pretty much until we find something, and then it will send a request. All right. So this one, we get the block, right? Convert it to a string. We check if the start. Sorry, we start at 0. Okay. And yeah, we just checking by adding 1 until the proof is valid. So this is pretty. This is not like the fastest way to do it, but this is just an example, right? Your proof starts at 0, and you're gonna hash it until you're gonna hash and increase +1, and then hash increase +1, right? Until it's true. When it finds the proof, it stops, it prints out this, right, and returns. When this returns, the request will happen, but yeah, we'll get to that. So let's just go over like the boilerplates. All right. So if we're calling this file, we have some arguments here, but it doesn't really matter. It's just change the server. And then we're reading a file here which just has my name on it to simulate like an account. All right. And then we start mining. So while true, we get the last block from the chain. Try getting the data out, right? And start working on the proof of work, right? When this function returns, we have a new proof, right? So we have something that is valid. So we're gonna send it to the mine endpoint. The server is obviously also gonna check if it's valid, okay? And if the message is new block forced, it's we got a coin. Otherwise, it's invalid. All right. Questions about this part, the client side, the whole thing. All right.
Yes.
Yeah. Go ahead.
Like the code looks too good. Like, how much time did it take to do everything?
Yeah, it took me the whole afternoon for sure. It's kind of a, I think it was a 2-day project, right? Victor, I don't know. I think it was a 2-day thing. And it had more to it. It didn't just have this. It had like transactions and things like that. Right?
Yeah, I think so. I think on Friday we had to build like a front end kind of thing where you could interface with the server, right?
Yeah. But that's the sprint. That's even more, more stuff. Yeah. But yeah, it was Wednesday and Thursday project, and this is like the Wednesday part. All right. And yeah. All right. So let's get it working. All right. So let me start this. I've already like did ppm shell, ppm install, things like that, right? I'm just gonna run the server here, and I'm gonna run the client on this side, and hopefully it mines stuff. All right. So yeah, it is mining. All right. So as you can see, like 3 zeros is very fast to find something that matches. All right. Is there anything specific you want to try? You want to try like changing the proof with something else and see how much coins you get? Any suggestions?
17 zeros.
That's gonna take a while. That's gonna take a while for sure.
Actually, you are not showing the hash. If we could see it to see
Yeah,
like the
okay.
zeros at the end.
So let's see. Do you want to see all the attempted hash or just the ones that are
I
valid?
guess the attempted ones would be too fast, so no. So
All
only
right.
the.
So let's see. Well, I just go to the client side. And yeah, basically every time we get a proof, maybe here, yeah. Nope, back here in the proof of work. Oh yeah, the hash is inside here. It's not really that easy again. Let me see.
Should
Maybe
do
on
it
the
after
server
the
side.
while. Maybe.
Yeah, I'll think I'll check on the server side though. Because, let's see, valid proof, and we check the hash. All right, so print yes hash. So attempted like this, and I'm gonna restart. All right. Yep.
Wait a minute. It's in the beginning?
Yes. Yeah, it is. Maybe I said it was in the end. It's not. It's in the beginning. I did it like this, right? So from 0 to 3, excluding the third. All right. So that's these 3 zeros here. All right.
Cool.
So yeah, that's that's everything we had for blockchain. Is there anything else? Any questions? Anything else you want to see about this?
Can we get access to the code?
Yes. I'll share it right now. Yeah. Maybe I'll just drag these.
I guess we can also share the actual repo just in case you want to try it out yourself, like the Lambda school repo, that you can fork and clone.
Yeah, like the project one, the old project. Yeah. Okay, so I'm gonna stop mining because I get too many coins.
You could be rich.
All right.
Yes.
Let's see. Yeah, it's remote. Yeah, I don't have it here though. Yeah, we'll share. We'll share this, and we'll share the let's say the exercise, right? So I guess if you want to do the exercise by yourself, don't look at this, even though we've already did. So, but yeah,
I want to play with the code because doing it from the beginning will take forever.
yeah, yeah, and that's also why I didn't do it right now, right? Because like all of this stuff, yeah, it takes time, right? So, all right. I think yeah. So if there's no more questions, we'll just go over the resources we talked about and share them, and you'll also get the recording of this later on. Yeah. Anything else?
I just posted the link to the Lambda school hash blockchain thing. It's in the CSEU4 underscore AH channel.
Nice. Yeah. Um. All right. I think we can end. Is that fine, Victor? If you anything else? No?
Yeah,
All right.
that's
All right. Yeah. All right. I guess I'll see you all tomorrow in the sprint challenge. So yeah.
okay.